All right, how's everybody doing? Welcome back to our Math for Healthcare video lecture series. We're going to continue on with our discussions and exploration of binomial random variables and their distributions. All right, so let's suppose a virus infects someone who comes into contact with probability 0.02. All right, 2% chance. Suppose 50 people come into contact with, suppose 500 people come into contact with the virus, and we'll let Y be the number of people from that 500 that are infected. Is Y a binomial random variable? Let's see here. Do we have a fixed number of trials? Yes, right? We have n equal to 500 fixed trials. And two outcomes, yes, infected for each trial or not infected, or each person, right? And lastly, are they independent? Okay, yes, because that probability 0.02 doesn't change depending on which person you are there. So yes, because my probability of success, right? Success here is getting infected. 0.02. Okay, so yes, it is a binomial random variable. And in fact, we could go to Desmos real quick. And before we move forward with that problem, we get an idea of what this distribution looks like. So let's see here. We have 500, 0.02. I'm typing this in. Think about, okay, where is that going to be? Oh, yeah. Right, that was an interesting thing, right? It's saying, and let's take a look quickly, zoom to fit. No, it's real skinny. All of the bigger probabilities that are any meaningful greater than 0 are all over here. If we zoom in, we could see where is that? Somewhere between, looks like between 10 and 20 people out of the 500 is where our most is. And of course, what? That also means we're going to expect this expected value of our Y to be somewhere over there. All right, so let's see here. We have two questions to answer on that. We want to know, what is the probability at least 10 will be infected? Okay, so that first question is asking what? Find the probability that Y is greater than or equal to 10. All right, and we could go to Desmos here, and we do our B, let's see, B dot, and here it says CDF, right? We want greater than 10. 10 to 500. Notice it's only, surprisingly, about 54%. All right? That's greater than or equal to 10 is only 54%, even out of the 500 people. All right, so from 10 to 500. All right, now how many people do we expect to get infected? We don't really need Desmos there, right? So we're looking for the expected value of Y is number of trials, 500, times probability of success, 0.02. And I think that comes out to be 10 on the nose, right? Let me double check that. So 10. Okay. All right. Good. And let's just put that in there so we could take a look at it. Here's my Desmos, and as you remember, where's most of the area? It's over there close to 0, not by the 500 side, and if you wanted to scroll all the way out, we could. Sorry. All right, there it is, all the way over there, and our expected number of people that we expect, the expected number of people to get infected is 10, and remember the units, 10 people. 10 people. Okay. So now, let's see here. We got a small healthcare clinic. There are 150 total patients, out of which 40 are diagnosed with hypertension, 30 have diabetes, and 15 have both hypertension and diabetes. The clinic is conducting a study to select a random sample of 20 patients for a research project. Calculate the probability that exactly 5 patients in the random sample have both hypertension and diabetes. Okay. All right, so let's think about this here. First of all, we need to define a random variable. Here we'll say let x equal number of patients in sample of 20 with both hypertension and diabetes. Okay, now we want to find, well, we want to ask ourselves, right, is this binomial? Let's see here. So we have a fixed number of trials. Yes, right, we do have that. What is that? N equal to 20. It's the sample size. 2. Yeah. Have both or don't. You either have both diabetes and hypertension, or you don't have both. Okay? 3. Independence. Independent trials. So here, let's see, what do we got? Clinic. No. Are they independent? Do you see this? No, right? The probability is going to change if the first person you select has both diabetes and hypertension. No. And in the end, what is that? When we have the fixed trials and both, and that success or failure for each trial, but not independent trials, we have a hypergeometric distribution. Okay? So that means that we can't quite just use our binomial distribution in there to find this. But here, we will say that, let's see, what do we got? Remember, we got to find the size of the sample space. It's going to be 150, choose 20, right? Okay. And now what's our numerator? This is how many ways to choose a group that of 20 that has 5 with both hypertension and diabetes. Well, we got to choose 5 from the 15 with both. And then let's see, there's 150 total, so 135, and let's choose 15. Now we want to use our calculator to calculate that, or Desmos to calculate that, right? We don't want to do that by hand. Let's see here, we got... We're choosing 5 from 15 and another 15 from 135. Okay, you can see that's a big number, but we're dividing by just in general with everybody together in one bin. So the 150, choose 20. Ooh. 150, choose 20. And it looks like it comes out to be about 2.5%. So that's the probability that exactly 5 of these patients in this random sample have both hypertension and diabetes. Okay. Now, let's see here. One thing I want to know, what if it asks for what's the expected number of people to have both diabetes and hypertension of this sample of 20. Now, remember, this isn't binomial, right? So anything that wasn't binomial, find the expected value, we need the whole probability distribution. Here, that's going to be, we'd have 20 different entries, right? You could have 0 people with both, 1 person, 2 person with both, 3 person with both, all the way up to 20 people. Well, not 20, up to 15 people with both. All right, so that'd be a lot of work. But it turns out, when we find the expected value of hypergeometric, we could do it very similar to how we do the binomial expected value. So here we could find it by the number of trials times the probability of success on the first one. So this is going to be 20 times, what do we got here? 15 over 150. And it looks like that comes out to be 2. Two is our expected value there. Okay. Good, but it's important to notice that it's hypergeometric, it's not binomial. All right, we can't use the binomial distribution for this one because it is not a binomial random variable because we don't have the independent trials. However, there is that sneaky way to get the expected value. If you're curious about it, I could show you that some other time on your own. I'm happy to make a video separately, but it's not necessary for this class. All right, now suppose we have a pharmaceutical company that's conducting a clinical trial to test the effectiveness of a new medication in treating a specific condition. The trial involves administering medication to patients and observing whether their symptoms improve after 1 month. The company expects that the medication will be successful in improving symptoms for 70% of patients. If a random sample of 225 patients from this trial is selected, what is the probability that exactly 170 patients show improvements in their symptoms after taking this medication? All right, so first of all, let's define a random variable. What are we talking about? We want to know what? Y equals number of people from our, how many? 225 that the medication is successful in treating symptoms. And what are they asking for? They're asking for the probability that y is equal to 170. All right, now I want you to check for, is this binomial? What are our conditions? Fixed number of trials? Yeah, 170. It's either successful or it's not successful. So we got only the 2 outcomes for each trial. Lastly, are they independent? Again, this is saying 70% for all the patients, so it's not changing depending on the patient. So yes, so we end up with y is binomial with n equal to 225 and p equal to 0.7 or 70%. Okay, so let's go take a look at this distribution. I'm going to go up here. I'm going to change this to, let's see here. We now have how many? 225. And 0.02 is going to be what? 0.7 now. All right, my n is 225. My probability of success p is 0.7. All right, now this is what our distribution looks like. Okay. And notice here, so what do we have? Probability of success 20% or 70%. So it's shifted over to the right a little bit, right? Where that peak is. And we want to know, we want of a single number exactly 170, so b.pdf, probability density function, for y equal, for how many successes again? 170. And that comes out to be about 1%, 0.011. Okay, yeah, so the probability of exactly 170 people that has successfully improving symptoms from the medication is 0.011. What is the probability distribution for the number of patients improving in the symptoms? Again, we just looked at that, right? Just as a reminder, this is what the distribution looks like. And shift it over to the right a bit. Pretty small, that it's only works for 100 people or so. Pretty small probability. How about the expected number of patients that see improving symptoms of the medication? Okay, so the expected value of y, this was a binomial. So we simply do our number of trials times the probability of success, and that is oh 157, and that's 157.5 people. Okay, and that makes sense. If we look at our picture real quick, 175 is over there by near that peak, right? Okay, so we'd expect 157.5 people to see improving symptoms, and notice we leave the 0.5, even though a half a person can't get have improving symptoms. We leave the 0.5 because it's a long-term average, all right? What do we think about this medication, and what other factors might we consider? All right. Well, let you think about that a minute. Remember, hit pause, go ahead and think about it. Maybe write some things down. And as far as me, if I saw a medication like this, here's part of it. It's pretty good. 70% is pretty high. But what do I think about the medication? Well, I think other factors are important to consider. Number one, are there any adverse reactions from the medication that they knew of? Is there a percentage on that? The other thing is, are these symptoms that can be improved through lifestyle changes, say exercise or diet? Those kinds of things. That's also going to affect what I think about the medication. Now, it's not so important what I think. It's more important, I want you guys to think about it. What do you think about these probabilities? And if you saw this in a paper or something like that, what would you think? All right. Let me know if you have any questions, and have a great day.